Okay, guys, welcome. Today we're going to talk about assessing risk. Okay, now the first topic that we're going to talk about is the idea between risk and travel. Now, the idea of travel risk is usually expressed in terms of what's called an accident rate or a death rate. Now, suppose an annual accident rate is 750 accidents per 10,000 people. We can then think of this as a relative frequency probability, which we could express as 750 over 10,000, which would, of course, give you a probability of 0.0075. Okay. Now, a figure in the textbook, which I've copied here, shows the number of automobile fatalities and the number of deaths, number of miles driven among all Americans per year from 1970 to 2011. Now, in terms of death rate per mile driven, we want to look at how the risk of driving has changed over this period. Now, the vertical bars here represents the number of deaths, right? So you can see that in general, they're sort of decreasing, right? And of course, this blue line here that's coming across this line right here represents the vehicle miles that have been driven, right? So what we have here, and of course that's this axis right here, right? And then the other axis would give us the deaths. So you can see that driving has gone up while accidents have gone down. So in terms of miles driven, the number of accidents has decreased even better than what the vertical bars represent. Right, because for example, in let's say 1970, let's just say that we're at 50,000 deaths, and it looks like the vehicle miles driven was about 1 million. Oh, this is trillion, right? So it would actually be something like this, right? Well, these three zeros cancel out with three of these, and then I'm essentially taking, I actually need, let's see, that's thousand, million, billion, so I actually need three more zeros here, right? So this is going to give you, let's see, so we're going to get, so when all is said and done, we're going to have 5 over 1, and then so 100 billion, right? So you're going to have point and then a bunch of zeros and then a 5. Now, that might seem like a very small number, but if we compare that to, say, 2011, when now the miles down here is about 3 trillion. And now we have that let's see, that the number of deaths is around 32,000. Right? So you're going to see that this is actually going to decrease a lot because we're going to be down to, once these three cancel with these three, we then have 32 over 3 billion, right? And of course, once you were to plug these numbers into a calculator, you would find that the death rate has drastically improved based on this graph. Okay, now in the next example, we have that for the 11-year period from 2002 to 2012, the total number of deaths in commercial airplane accidents in the US was 153, or on average about 14 deaths per year. By the end of this period, the total number of miles flown by commercial aircraft was about 18 billion per year. So we're going to use these numbers to calculate the death rate per mile of air travel, right? So we have 14 deaths per year. And in the bottom, we have 8 billion. Right? Now, if you were to calculate this, you're going to get an extremely small number. We'll actually do this. 14 divided by 8 billion. And we get this is 0.000000002. Right? Now, if you compare this to the risk of driving, right? For example, we have, let's say now we have 32 deaths per year over 3 billion. All right, and if we compute this, 32 divided by 3 billion, you're going to get 0.000000011. Right, and if you count my zeros, hopefully I did it correctly, you're going to get that this number down here is bigger than this number. Right, so of course, this agrees with the popular notion, because it's of course true, that you're actually safer flying than you are driving a car, even now. Okay, now the next thing we'll talk about are what are called vital statistics. Now, vital statistics are used for a variety of reasons, and they give data concerning births and deaths of citizens. So there's a set of vital statistics that's shown in the textbook, which I've copied right here. Okay. Now, in this next example, we're going to assume a U.S. population of 315 million. We're going to find and interpret risks per person and per 100,000 people for accidents and suicide. Okay, so for example, let's look at accidents. So we have 122,800. Now, if we want to get this per person, then we would need to divide this by the number of people. So we need to divide by 315 million. All right, so if we calculate this, 122,800 times 315 million, we get that this is 3.8682. Wait a minute, I did times, so I don't want to do that. So let's erase this and let's try again. So 122,800 divided by 315 million. Okay, and then that gives us 0.0003898. Why isn't that copying? 0.000389841. Right, so that's the percent chance per person for one of these, right? Now, how many of these would it be per 100,000 people? Well, we would just multiply this by 100,000. And if we do that, we're just going to be moving the decimal place over a couple times, and we're going to get that this is 38.98 roughly, right? So per 100,000 people, you would expect almost 39 to die from an accident. Okay, so this was for accidents. And of course, for suicides, the same calculation. All right, nice joyful topic here, but nonetheless, so we have 38,300. And again, divided by 315 million. So if I do 38,300 and divide it by 315 million, we're going to get that per person, this is 0.000121587. So then, of course, per 100,000, we're going to get about 12.16. Right? So out of 100,000 people, you could expect 12 to die from suicide. All right, so that's sort of the idea here. Okay, now a very common vital statistic is the life expectancy, which compares the overall health at different times or locations. Now there's two graphs in the book that show different types of life expectancy trends. So the life expectancy is the number of additional years a person of a given age can expect to live on average. All right, so that's what we mean when we say the life expectancy. So here's two graphs that sort of showcase some of that idea, and we're going to do an example with that. So now using this figure, we're going to find the life expectancies of a 20-year-old person and a 60-year-old person, and are the numbers consistent? Well, the life expectancy is the second graph that's given. Now, if a person is 20, I would have to go to where 20 is. Oops. And I need to find out, well, where does the graph intersect with this 20 right here? Now, if we go over, it looks like a 20-year-old can expect to live an additional 60 years, right? So then that would give us 80 years old. Now, if we go to 60, and we go up to the graph here, it looks like if we come here, find our graph here, and we go over, we're going to be slightly higher. We're going to be about 25. So it looks like we get an additional 25. So if you made it to 60, on average, you can expect to get to 85. So the numbers are somewhat consistent, but they're off by a couple years. And the reason why is because if you made it to 20, you haven't made it as far as someone, obviously, who's made it to 60. And by making it to 60, you sort of guaranteed 40 extra years of health, right? So that's sort of the idea there. That's why that life expectancy is coming out a little bit different. Okay, now in the next example, we're going to determine how much life expectancies rose during the 20th century based on this graph. Now, we're also going to suppose that life expectancies rise by the same amount during this century. And of course, what will the expectancies at birth be for children born in the year 2100? And what would the implications be towards our own life expectancy? It could be something to think about. Okay, now if we look at this graph, it looks like from 1900, our life expectancy started down here. And of course, it's different for men and women. But in 1900, it looks like the average male could live to about 46, whereas the average woman could live to about 48. And then based on this graph in 2010, it looks like men have jumped to about 77 and women have jumped to about 81. Right, so now what were these increases? Well, to go from 46 to 77, I guess I would need 27 plus another 4. So it looks like we're having a 31-year increase. Right, and then it looks like to go from 48 to 81, it looks like that would be a, what is that, a 33-year increase, right? So then if we sort of round this to 2100 and we just say that we increase by the same amount, if we were to increase this by 31, this would then be a 108. And this would be, if we increase it by 33, we're going to get a 114. So if the current trends were to continue, right, or if the similar trends were to continue, then the male average life expectancy would be 108 and the average woman life expectancy would be 114. Okay, so the implications for your own life expectancy, right? So as we continue to get further and further in the future, right, we can expect this to go up. So what does that mean towards your own life expectancy? Well, if you were to look at your life expectancy now, right, if you were to live another 20 years, your life expectancy would probably be bigger, right? That's exactly what this is saying. Okay, so that concludes this section on assessing risk. I hope you enjoyed, and I will see you next time.